Okay. Homework 12 is due on Monday. I've already got some good questions on that assignment. It sounds like you're working through some of the water surface profile ideas. Remember that the Darwin Designer assignment is also due. Now, I got a good question that I need to address for everyone. On the Darwin Designer assignment, stick only to the pipe diameters that are on that handout. Don't interpolate in between. So, does anyone have that assignment handy? All right, so it says, for example, the pipe sizes that are available are 100, 150, 200, 250. So don't assume that a 225 millimeter pipe is available and that its price is between 51 and 60. Stick only with these prices and these pipe diameters. And these are, I'm sure you can have custom sized pipe made in whatever diameter you want if you're willing to pay for it, but those are just some typical sizes that would be readily available. So that assignment's due on Monday. We're going to continue our discussion of the numerical integration method today. Question?
The elevation of the reservoir is fixed. It's assumed to be fixed, right? We don't vary it in the optimization process.
That's right. The reservoir you can just leave fixed. Yep. Okay. And I think as far as elevations go, I didn't specify elevations for the junctions, did I? No. So they're all at 0, and the reservoir is at whatever above 0 and is fixed. All right. Numerical integration method. Remember what it's doing is it's applying the process equation at the midpoint between two places where we're trying to predict the depth. So if we have some channel and the water surface is varying, what we will do is we'll have a Y2, a Y1. If conditions are subcritical, then we work upstream. We're trying to predict what is Y1, and this method relies on us applying these calculations at the midpoint. So halfway between the two, we're going to find all these geometric parameters, the slope of the energy grade line, and so on. So I'm going to give you a demonstration, and then after the demonstration, you're going to be able to go through and work the in-class exercise that goes with that. So here are the steps I'm going to be following through and the things I'm going to be calculating. I'm going to find the dy dx at the midpoint, and so I'm just going to call it this function f at the midpoint where x bar is halfway between, in the horizontal direction, the two depth places of interest for depth. Y bar is the depth at the midpoint. So I'm going to find the slope of the energy grade line at the midpoint. The channel slope is constant between the 2 points. And I'll find the Froude number. This bar means at the midpoint. So I've defined what I mean in terms of the horizontal distance, and the depth at the midpoint will be the average of the two. And if the example has subcritical conditions, I'll move upstream, calculating Y1 as Y2 minus this process equation times the difference in distance between 1 and 2. And then I'm going to be calculating all of these different parameters at the midpoint, and it's an iterative equation where an iterative process, and I know that I've got the correct upstream depth that I'm trying to calculate when my initial guess matches the calculated value. And so I'll demonstrate that process so you get a sense for what it looks like. And just to flip forward in the notes, you'll notice that there is on the final page, some empty squares here that show basically the format that I would use in setting up an Excel spreadsheet to solve that. Okay, we have a rectangular concrete channel. It's carrying 10 cubic meters per second. The channel is 5 meters wide. The slope is given. Just as the preliminaries, I'm going to find the critical depth, the normal depth, and the water surface profile type, just to get things started so that I know if it's getting deeper or shallower in the direction of flow. Okay, critical depth, y sub c, is going to be the flow per unit width. The flow rate is 10 cubic meters per second, and the width is 5 meters wide. So that's basically 2 meters squared per second, squared divided by g and to the 1/3 power. Okay, from that I get the critical depth is 0.742 meters. The normal depth, I'm going to use normal depth versus critical depth to know if the slope is mild or steep. All right. So the normal depth I solve basically using Manning's equation, where I've got 10 cubic meters per second is equal to 1/n times the area, 5 times y sub n to the 5/3 power. The wetted perimeter, 5 plus 2yn to the 2/3 power, and the channel slope to the 1/2 power. Okay, we solved Manning's equation using Excel in class last time. It took us a little bit longer than I expected. I guess it's good that we got our practice. In this case, I'll just put the magical solver, assuming that there's some really quick, easy way to find the normal depth, maybe with the calculator or something, 1.124 meters. Okay, you've gotten some practice classifying water surface profiles, and what you should do is you should compare the critical depth, the normal depth, and the flow depth at some point of interest. And our point of interest, the present depth, is 0.8 meters. And so if we have our channel cross-section, which is already drawn here, where we know the depth, it is 0.8 meters. The normal depth is 1.1, so it's up here. Y sub n is 1.124 meters, and the critical depth, 0.7, is down here. And y sub c is 0.742 meters. And so the flow depth is in zone 2. Remember, zone 1 is above the top line, whether the top line is critical or normal. Zone 2 is between the two lines, and zone 3 is beneath the lowest of them. So normal is above critical. That means we have M, and we're in zone 2. So this is an M2 profile. An M2 profile is caused by flow over an edge, like is depicted on the screen there. I guess that was a bit of a giveaway, me providing that diagram, but we've got an M2 profile. But that's how and why we got it's an M2 profile. So the first three things, check, check, check. Not too hard. Finding the depth 50 meters upstream is going to be a little bit more tricky, though. Any questions on this part of it before we get into finding the depth upstream? All right. What I'm going to do is open up that spreadsheet template that is on the last page of the notes. Okay, I've got all the equations that I need on there. I've already keyed in the flow rate, the channel width, the slope of the channel, our given n value, and then since it's subcritical flow, I'm calling the known Y2, meaning that we're working upstream to find out what's the depth some certain distance upstream from where we're at. All right, so the distance between the 2 points. In the problem statement, it says that we want to find the depth 50 meters upstream. And so the full distance here of 50 meters isn't what we're going to be using as the distance to the midpoint. The full distance of 50 meters means that the distance to our midpoint, x bar, is 25 meters. All right, so 50 meters is the distance between them, and so the horizontal distance to the midpoint is going to be distance divided by 2. Now, I have to start off with some guess depth upstream. And remember, from the water surface profile, I know it's going to be deeper upstream. I don't know how much deeper. I know that the normal depth, eventually, it's going to keep getting deeper and deeper and deeper until it gets to the normal depth. So it's going to be somewhere between 0.8 and 1.124. So in the description of the process steps, it says just to use the initial depth as the depth downstream. So just to illustrate, 0.8, although I know it's going to be deeper than that. Okay, so y bar, the depth at the midpoint, that's going to be the average depth between the two, is going to be y1 plus y2 divided by 2. So let's just make sure that works. If I had guessed that my upstream depth was 0.9, then it should say the depth at the midpoint is 0.85. And that's what it does. So everything's fine so far. Any questions up till now?
So on our sheet, it has y1 up top and y2 on the bottom.
Yeah, that's because in the example you're going to be working, in this in-class exercise, you're actually working on a supercritical where you're going to be flipping the known and the unknown. In this case, it's subcritical, and so the known value is the y2 and the unknown is the y1. Good question. Okay, so area, for this being a rectangular channel, at the midpoint, the area is just going to be the depth at the midpoint multiplied by the channel width. That's the cross-sectional area. It's a rectangle at the midpoint. It's just that the depth is halfway between the depth at 1 and depth at 2. I hope everyone's able to visualize that geometry. The depth is gradually increasing. Here I know it's 0.8. At 1, I've just made some guess for what the depth is. Right now, the guess that I've got keyed in is that value of 0.9. And so that means at the midpoint, the depth will be 0.85. It allows me to calculate the area. Wetted perimeter, remember, is just 2 times the depth at the midpoint plus the width. So that's how I do the hydraulic radius. Now, you don't have to be following along on your spreadsheet. If you just want to watch this one being done, that's fine. You're going to get a chance to try it out real soon. Of course, you can if you like. The hydraulic radius is the area divided by the wetted perimeter. Okay, the slope of the energy grade line at the midpoint means we're going to have to solve Manning's equation. And here, Manning's equation is written in terms of S sub F bar. So it'll be the N value times the flow rate divided by area divided by hydraulic radius to the 2/3 power. So I'll say to the 0.6666667 power. And now all of that is squared. So this gives me the slope of the energy grade line at the midpoint, based on Manning's equation. Velocity at the midpoint will be the flow rate divided by the area. The Froude number squared, we've got the equation here. One way of writing the Froude number squared for a rectangular channel is just v squared divided by g, 9.81, divided by y at the midpoint, because this is the Froude number at the midpoint, so the depth we're going to have to use is the depth associated with what's going on at the midpoint. All right. Now, this f, x bar, y bar, that's this equation here. So let me drag it down so we can have it on screen as I type it in. It is the channel slope minus S sub f, channel slope minus the slope of the energy grade line at the midpoint, divided by 1 minus the Froude number squared. And I've already got this Froude number in terms of Froude number squared, so I don't have to square it. It's already built into that cell. And then finally, the y1 depth we estimate what the depth is up there by saying it is y2 that is known minus this equation times the distance. Okay, so I know I haven't got the right answer because my initial guess isn't equal to the final depth. So remember how I said maybe as a first guess you can say 0.8? Well, that's worse. And so I'm going to go through this optimization process if I want this guess and this computed value to be the same, 0.95. It's getting awfully close now. 0.945. Okay, and of course if we wanted to use goal seek, one easy way to do goal seek is to have a difference, DIFF. So you're saying we want the difference between this and that, we want the difference to be 0. And so if I had had this initial guess as 0.8, now I can make it an automated thing by going into the what if analysis, goal seek, and what I would like is for the difference to be 0, and it has permission to change this guess depth upstream. Go ahead and change it, and then it converges on the computed upstream depth. And so according to the numerical integration method, what I've done is I've said I'm going to choose some segment that's small enough that I can assume the water depth varies linearly between those 2 points. And assuming that it does vary linearly, then based on conditions at the midpoint, I'm going to interpolate what that, or extrapolate what that depth upstream will be. The depth will be 0.945. All right. So any questions about that process that we've just jumped through?
Dr. Wade, area, this is a rectangular.
This is a rectangular channel.
So A bar is essentially X bar times Y bar.
No,
Oh.
A bar is going to be the channel with B times Y bar.
Oh.
Because remember, X bar is the distance along the direction of the flow path upstream. So X bar was 25. It's the width of the channel that's going to give us the area we need. Other questions? All right, I know you're raring to go. So that is the only demonstration that I wanted to show you on how to use it. You've got the handout, and then you've also got this in-class exercise. I'm going to be circulating around, and what I'd like you to do is analyze what's going on after the gate. And so in this in-class exercise, we've got an M3 profile, meaning that we know it's a subcritical slope, which means a mild slope, and we're in zone 3. The actual depth is below both the critical depth and the normal depth. And so we are going to try and find the length of the rising curve, assuming a single step. And so that's going to be a little different from what I just showed you, because in part A of this in-class exercise, the two depths are already known. Both y2 and y1 are known, but what we're trying to find out is what distance is going to cause this spreadsheet to converge. So in other words, in this in-class exercise you're going to be working, rather than trying to find the unknown depth, you're going to be solving for the unknown length. And so you're going to be changing around the distance until the unknown depth matches. All right? So we've got supercritical flow, so be sure and use the correct equation, set it up so that you're solving for y2, even though y2 is known. The y2 is going to be this 0.55 meters. All right, I'll turn you loose on that, and I'm going to be wandering around answering questions as you set it up. So in part A, if we do that curve in a single step, we're going from 0.25 to 0.55, we find that the length will be 53.75 is the distance it's required for it to increase the depth up to there. If this is a really curved surface, then it's not good for us to approximate it as a line, and we should break it up into more pieces. And so sometimes the question arises is how many steps should you have for a water surface profile? And there's no hard and fast rule. What we can do is we can see if if we get very much difference by doing it in 2 steps. And so by breaking it up into 2 steps, I said we'll go from 0.25 to 0.4 and find that distance, and then go from 0.4 up to 0.55 and find another distance. Adding them together, the sum of the 2 steps is 53.18, and when we did it just in a single step, it was 53.75. And so that's a very small difference between if we had broken up this profile into 2 steps versus doing it in a single step. And so that tells us that probably just a single step between these 2 locations is adequate, that there wouldn't be any need to further subdivide and try and shoot for more accuracy, because it's already a pretty close guess. All right, so once you've finished those 2 parts, then you're free to go, and I'll see you on Monday. Otherwise, I'm going to continue to be present and help people troubleshoot spreadsheets and all of that.